I'll write that. So x-axis is nothing but inputs. X, we denote it as x. And y-axis, time or space, time complexity or space complexity, anyone I'll be trying to model out. So I name it time or space. Now can anyone say how an average case curve can be there? Right, I'll choose one color here. And first I'll draw. Yes, somebody is coming. Yes, how?
Straight lines.
Straight line. No, now no curve can go in a straight line. Why? Because all the equations are not in a straight line. They are not linear. They are always curvilinear. So we cannot draw a function purely in a straight line. So surely it will be curvilinear. So this is my f of x function. So what I have to find is I need to find another function named as this. This is nothing but c1 into g of x. So now you are understood. Previously I wrote it as c into g of x for worst case and best case. Now I wrote c1 into g of x. Now what I will write next, you itself can say.
C2 into G of X.
Very good. I'm going to write it as c2 into g of x. That will be coming here. This is nothing but c2 into g of x. So that's great. Now we have here. Now can you say the definition? Let f of x and g of x be two functions. Yes, you can say that. And we missed here one. We missed this. What is this intersection
F of
point?
x equal to
What is this intersection point?
K.
Yes, K.
Okay.
The point, as Sirisha said, it is correct, but it is not only K, it is actually two terms, K1 and K2. I write both here, but in this case, I made K1 equal to K2. This is K1 as well as K2. Both are available here. Whether the two Ks are somewhat okay. Yes, K1 comma K2. Both are there here. K1 comma K2. According to this function, here K1 and K2 both are equal. After that, if K1 or K2, C1 into G of x is always greater than f of x, and C2 into G of x is always less than f of x. So that's what we are going to say here in the theta notation. So we'll go with the definition. Yes, you can say that. What is the definition?
Let f of x, g of x be
Yes,
two
let f
functions.
of x and g of x will be two functions. Yes, I wrote that. Be two functions. Yes, I wrote that. Next.
f of x equal
Constant
to
c.
Okay. F of x is equal to,
theta of g of x.
okay, theta of, you want me to write theta? I don't have theta symbol here, right? Theta of,
G of.
yes, exactly. Great. Theta of g of x. Yes. If f of x is equal to theta of g of x,
Constant
There exists a constant
C1 and
C1,
C2.
C2.
if there exists a
Constant.
constant, how many
C1 and
constants?
C2. C1 and C2.
C1 and C2.
Yes. There exists a constant C1 comma C2 both greater than 0.
Greater than 0.
If they are 0, what will happen?
And K1 equal to K2 greater than 0.
No
If
function.
C1 and C2, g of x will vanish if C1 and C2 are 0. Yes. And K1 comma K2 greater than or equal to 0. Such that I write it as C1 into g of x or I can write C2 first. So I can go with C2 into G of x less than or equal to f of x
F of
less than
x
or equal
less
to
than or equal to
C1 into
C1 into
G
G of
of x. If this condition is holding, then I say that it is an average case notation. This is an average case notation. The important point to note here is this k value. We cannot say that always this k1 and k2 will be the same, so that after a particular point c1 into g of x will be going in the upper bound and c2 into g of x will be going in the lower bound. I cannot assure that. Most of the time k1 and k2 will be in the different positions. At that time you need to take the maximum k value, right? Because at that point both c1 and c2 will be following the average case notations, right? So on the whole, what we are going to write here, theta notation is also
is
called
also
as
called as
average
bound.
case notation. Right? It's also called as average case notation. Hope I made it clear. Right? Is it good?
Yes,
What
sir.
is theta notation? Yes. So now coming to the play, big O notation is f of x less than or equal to c into g of x. Big omega notation is f of x greater than or equal to c into g of x, while theta is c2 into g of x less than or equal to f of x less than or equal to c1 into g of x. With all the three asymptotic notation very clear without any doubts.
Yes, sir.
Yes. Now for saying the theta notation, it is very simple for me to use this space alone for little o notation. So little o notation is nothing but we mean little o. This is a little o notation, right? A little o notation we mean it is exactly equal to big O notation, except the fact that in big O notation we mean f of x less than or equal to c into g of x, right? In big O notation we say that equal to is also allowed. What is if equal to is allowed? What will happen? In the same line as f of x, c into g of x also can exist. That's what it means, right? What is big O notation? Big O notation says f of x less than or equal to c into g of x. If this is happening, what will happen? At some point of time, I'm also saying that f of x is equal to c into g of x. Am I right? If f of x is equal to c into g of x, what condition will hold? Both f of x and c into g of x will be in the same exact curve. Am I right?
Yes, sir.
Yes. This hence that we call it as tightest upper bound. Tightest in the sense we are trying to fit a curve as close as possible to f of x. So if it is on top of f of x itself, then it is the best, right? The best mapping. So it is good or bad. If I map it exactly on top of f of x, then my function is the great, right? But usually in real time case, this is very difficult to get f of x equal to some c into g of x all the time, right? The exact same curve starting from origin to infinity. If I want to get c into g of x equal to f of x, it is very tough, right? So that's what is stated here. Little o notation is very easy, just to remove this equal to symbol. Now what is the case is f of x less than c into g of x. This is called as little o notation and also called as loosely bounded or loosely upper bound. We call it as tightest upper bound. What? Big O notation. So here it is loosely upper bound. It is little o notation, right? For here I say that for all k greater than or equal to x, c is a constant and c greater than 0, right? Am I making it clear what is loosely by upper bound or little o notation? Yes, I am making it clear what is little o notation.
Yes, sir.
Yes, sir.
Yes. Now you have to say me what is little omega notation. Straightforward.
F of x greater than or equal
F of x greater than
Very good,
c into
very
g
good,
of x.
very good, very good, very good.
to
So So I'll write the I'll draw the notation of little omega. Little omega is nothing but I'll draw here an omega notation. Yes. And here also it is f of x is equal to little o of, right? Here also I can write it like that. F of x is equal to small omega of g of x. So what is the condition for this to hold?
F of
What
x
is it?
greater than c into g of x.
Very good. And you need to, whenever you say the condition, please say with that k and the c values also, so that you will never forget. You'll get the full 3 marks or 5 marks. C into f of x, sorry, f is
K
greater
is
than c into g of x.
for all
For
x
all,
less than or equal to k.
yes, no, k greater than or equal to x. K greater than or equal to x. C is a constant
C greater
and
than
c
0.
greater than 0, right? That's a fact here. And I can also write here as f of x is equal to, can use directly this because O is a symbol. F of x is equal to, this is small o of g of x. If this to hold, then this is the condition, right? If little o notation is called as loosely packed upper bound, then what is little omega called as?
Loosely
Height.
lower bound.
Omega notation is
Loosely
loosely
lower
lower bound. That's it.
Loosely
That's it.
lower bound.
It is called as loosely lower bound. Yes. Now we are, hope you have gone through all the 5 asymptotic notations starting from big O to little omega, right?
Sir.
Yes. So far so good. Right. Now take a screenshot. We are going for a small revision on this. Revision is not question answer. Just I'm going to do. Take screenshot. Shall I proceed? Yes. Yes. I delete this. So on top, if you are answering for every thing, then it will be very nice. Asymptotic notations. So what is asymptotic notations is the first one. That's we have to write here. Okay. I'll leave that. Next coming to here. Notations. And this is characteristic. Condition. Also called this. These are the things we are going to write now. And you people are going to say answer for that. What is asymptotic notation? Quickly say the answer. What is asymptotic notation?
The representation for time
Very good.
complexity and the space complexity is
More
given
than
on
enough definition is that's it. The word time complexity and space complexity means a lot. We need an unique representation for specifying the time and space complexity of a given algorithm. And okay, change the color black. An unique representation for specifying the time and space complexity of an algorithm. This is asymptotic notation, a representation, right? So what is the first notation?
Big O notation.
big O notation.
Big O notation. Next,
Big omega.
Big omega notation.
second is big omega. Next,
Theta notation.
theta notation. Fourth,
Little O notation.
little
little
O
o notation. Fifth one
Little
is
omega.
Very good.
Little
Little omega notation. Yes, fine. Yes, symbol. What is little o symbol? Sorry, big O. Big O.
So
This
big
is omega. This is theta.
Theta.
This is
Small
little
o.
o.
small.
Yes, small o. And this is small omega.
Double E.
Oh my.
Not W, omega. You write in physics, right? Omega. That's it. Right? Characteristics. F of x is equal to
Plus
big O
G
of g of
G
x.
of
If this characteristics to work, what should happen?
F of x
F of x
less
F of x
is
less
does
than
not
or
equal
equal
to c into
G of
g of
to g.
x. Very good. Then for all,
x greater than or equal to k.
no, always you are repeating that. K greater than or equal to
greater
x.
than or
Sorry. It is k or
X
x?
greater
X
than
only, sir.
X, sorry.
X only.
X greater than or equal to k.
K.
You are correct. X greater than or equal to k. Next, C
equal
is a C greater than 0.
Than or
So this is the key, right? So good, super. X greater than or equal to k and C greater than. Okay, this we can write separately, right? Now coming to big omega, f of x
X equals
equal to omega of g of x. Omega symbol I will draw. Okay, omega. See, instead of x, I can also ask in question as f of n also. F of n is equal to big omega of g of n. Okay, so instead of x, I will write as n also. Okay, right?
Yes,
Yes,
sir.
sir.
Yes. So what will come here? F of x
Greater
greater than or
than or
equal to
greater than or
greater
equal
than
to
or
G of
equal to
X.
c
c into
into G of
g
x.
of x.
c into g of x. Instead of putting bracket, I can put like this also. C into g of x. For all
For all
x
X less than
greater than or
greater
equal
than or
to
equal
k
to K.
and
C greater
Greater
than.
than.
yes, c greater than 0.
Zero.
So this is what? Finally, to theta. C2 into, sorry, f of x is equal to
Theta of
Theta into x.
theta of
G of X.
g of x. Okay, I'll draw theta now. Okay, theta is ready. Condition
C2 into
Theta
G of
into
X
G of x
C2 into g of x
less than or equal to
less than or equal to
f
F of
of x less than or
less
equal
f
equal to
of x less than or equal to
C1 into G
c1
of
into
C1
g
into
of x. For all x greater than or equal to k, 1 comma k2 is equal
greater
to
than
max of k1 comma k2, right? X out of this, what is the max? After that, x to be greater. Okay, the largest of both k1 and k2. Okay, fine.
yes, sir.
Fine or confusing?
fine, sir.
Yes. Then c1 comma c2 greater than 0. So far so good.
Yes, sir.
Yes. F of x is equal to small o of g of x. What is the condition?
F of x
F of x is less than
Less than
less than
c of
C
into
k
G of
into g of x. For all x greater than or equal to k and c greater than 0. By seeing this itself, the entire by seeing this table, we should be able to study the entire asymptotic notation question. What is this?
f of x greater than c into G of x.
1 minute. You are very fast. 1 minute. Okay. F of x greater than c
C
into
into
g of x for all x greater than or equal to k and c greater than 0. Yes, we finish the 16 mark question. But you don't write like this, you write with definition. What is the definition? Let f of x and g of x be two functions. If like that on diagram that and all you should do. Okay.
Yes, sir.
Yes, this is if it is in a written examination, this will be a very big 16 mark. Okay. Now also called this. You remember like this big O means worst case like that. If one is you remembered correctly, na, others you can come very easily. O means worst case. Okay. This is worst case, and another name is
Tightest
tighter
lower.
upper bound.
Upper.
Very good. This is over. Now next. This is
Tightest lower
best case,
bound of the best case.
tightest
Tightest.
lower bound. Very good. This is average case,
Average case.
and no, there is no other no tightest or loose. I don't see. There is little O. Little O is actually worst case, but it is loosely
Loose upper bound.
upper bound. And this is loosely
Loosely lower bound.
loosely lower bound.
Average case, loosely uppercase, and loosely lower bound.
It's fine. Now we got the thing for everything. Now we are very well versed on how to use this asymptotic notations, right? By this table, we can easily understand the things. Now, something to understand from MCQ perspective or in gate perspective, we need to understand something more from this. Now, here, what is called as strict parameters we need to identify. Who is very strict? Which asymptotic notation is very strict? Those things we need to identify. Yes, by seeing this, we cannot identify, but by doing the problems, we can identify very easily. And you should understand like what is the tightest bounds, what is the loosely packed bounds. If I ask tightly packed bounds and give big O, big omega, and some other thing, you should think none of the above, like that you should be able to select, right? So this is the entire thing for asymptotic notation, and we have done it with much clarity, I hope, right?
Yes, sir.
Yes, sir.
Yes. We'll move.
Yes, sir.
Okay, this screenshot is most important. This screenshot can be helpful in studying also in asymptotic notations. Within a glance, you can
Sir?
study the 16. Yes, come again. Yes.
Sir, for little o notation and little omega notation, it is k greater than or equal to x, no, sir.
No, that's what somebody actually corrected me. It is not k greater than or equal to x. It is x greater than or equal to k. Somebody
Yes, sir,
actually
for
corrected.
little O, sir.
Yes,
Sir,
little
for
only.
little
In the
O,
previous, in the previous while teaching the little o, I put like that, right?
Yes, sir.
It is actually x. X should be greater than or equal to k. And correct there also.
Okay, sir.
Now only somebody told
Sir,
me
for
right.
all
It is not
same,
k
sir.
greater than or equal
For
to
all
x.
four.
It is greater than or equal to k. Come on.
Sir, for all four notations, same as sir, x greater than or equal to k.
Yes, for all 5 notations, the condition will be the same. Only the difference will come for theta notation, where k1 and k2 will be there and c1 and c2 will be there. Because it deals with two different bones at the same time. Any doubts in asymptotic notations? Yes, so far so good.
Yes, sir.
Yes. Shall I raise? You can take the screenshot. Shall I proceed?
Okay, sir. Next.
Yes. Next is my one interesting part, that is types of algorithms. And you say we already dealt this in the previous class. How many types I can represent a single algorithm? For example, Euclid. How many ways we represented Euclid?
2 years.
2 ways. Very good. What are those?
Yes, n.
Recursive.
Recursive, non-recursive.
Yes, recursive and non-recursive. That's what we are going to deal here. We are going to mathematically identify what is recursion, what is non-recursion, how to deal with the analysis of those algorithms, we are going to see here, right? So as one of the girls said, it is recursive or non-recursive. First, the simple one is non-recursive algorithm, also called as iterative algorithms. Why I call it as iterative algorithms? Huh?
Runs in a loop.
Yes, it is actually looping. If I use non-recursive, what is the meaning of non-recursion? For loop, while loop, do while loop, those things are actually used here. So it is actually a recursive algorithm. So it is a non-recursive algorithm which uses looping. Can anyone say, can I have a loop in recursive algorithm? I mean, can I have a for loop in a factorial program which uses recursion? Can I have or not?
Yes,
Yes, sir. Can I have or not? Yes. If you are saying the answer, please say fully. You can say so that I can appreciate.
Yes, sir.
How? For example, assume that I'm doing a recursion equation, right? For example, I'm doing an Euclid's algorithm. If I was running a for loop, what will happen? It will become a double loop. For doing a single operation, I'm doing double looping operation. One is normal iteration. Recursion function by itself will perform looping only, right? A function that calls itself. So the same operation will be happening again and again. So for performing that same operation, we don't need to go for a loop. Instead, we can have a recursion itself. If you want that recursion to happen iteratively again, then you can have a looping, right? So that's the difference. So one function, one kind of algorithm is non-recursive algorithm. Other kind is recursive algorithm, which uses stack, right? So recursive algorithm uses stack data structure. Uses stack data structure. Now we are going to see some kind of examples for each of these algorithms, and those are here. What are the algorithms we are going to discuss in non-recursive side is, first one is finding max element in a array. What the first one we are going to see, finding max element in an array. Second, checking whether the array is unique. What is unique? In unique array, can anyone say what
Different.
is unique array? Unique means what? For example, I say the array 1, 2, 3, 4, 5. I say the array 1, 2, 3, 4, 5 elements. 5 elements are there. Whether this array is unique or not. What is unique? All the elements should be unique. Means that no elements is repeated. So array A is equal to 1, 2, 3, 4, 5 means that all the 5 elements are unique and not duplicated or repeated. So I can call that array as unique array. Other array I can, if I have 1, 2, 3, 3, 4. Here the element 3 is repeated, so the array is not unique array, right? So that's what we need to check here in the next algorithm. That is most famous, that is matrix multiplication. Fourth is finding number of digits in binary for a given decimal number. That's what we are going to do. More than we know, we have already practiced the programs for these kind of algorithms in the earlier classes also. But our ultimate motto is not to write programs for these things alone. When we are going to write programs for all the algorithms, the motto for us is to calculate the time and space complexity for these algorithms. That's what our ultimate motto is. So how that we are not going to directly say it, we are going to derivate line by line the algorithm, and then we are going to say what is the complexity. That's what we are going to do, right? So these 4 algorithms are in one side with non-recursive algorithms. On the other side, we have recursive algorithms. One is First one is factorial of a number. Second, towers of Hanoi. Hope you have seen about this in data structure. Anyway, we will be discussing one more time what is towers of Hanoi. And anyone have seen this about what is towers of Hanoi? Anyone?
Sir,
Okay, we will discuss. Yes, Sirisha.
placing them in order, sir. Like, if they
What we are
given
going to
small
place?
to big, then we have.
Yes. We are going to place the towers
Yeah.
in some order. Right. Very good.
Yeah.
We will discuss. Right. Fine. And next comes the Fibonacci series. Finally, finding number of digits in binary for a given decimal number. Same as one of the algorithm in non-recursive case we are going to take, and then we are going to do in recursive also. So these four algorithms, four each, totally 8 algorithms we are going to discuss. We are going to analyze it line by line and find what is its complexity. Most possibly, we are going to find the worst case complexity. Why I was more eager on the worst case complexity is, if I was going for an algorithm, my ultimate motto is to understand what is the worst case. I need to identify how worst my program is going to go rather than how best it will perform. Because I know that my program is good, it is giving the output. By that itself, I understand that my program is good. But I need to understand how worst my algorithm can go so that I can rate my algorithm. So that I was more eager on the worst case. Not only me, all the algorithm analyst and the scientist will be concentrating on the worst case rather than average or best cases. Some ultimate aim is going to be make the worst case and best case equal, so that there will be no difference. That and all will come in randomization and approximation algorithms only, where the both worst and best case will be equal, right? That is and all ultimate algorithm sense. We'll discuss that also, right? Shall we proceed with these kinds of algorithms?
Yes, sir.
Yes, sir.
Yes. Before, yes, one hint I'll give here. The hint is nothing but items here. It not necessarily be said that all these algorithms can be done using recursion, right? I cannot say that if I have a non example for non-recursive algorithm, I will not surely say that that algorithm can also be done using recursion. I cannot say, because for some algorithm recursion cannot be applied. But items over here, I can surely assure that for programs which require recursion, I can also solve it using non-recursive algorithm. But you will not have enough memory. You need to waste the time. But these members will take memory into hand. What memory? Stack memory. It will take stack into hand and then solve. So they can be solved using iteration also and recursion also. But these guys, I cannot assure that they can be solved using recursion and all. Why? Because matrix multiplication. That and all, we need to identify how the recursion relation should come. Then only I can go for the recursion solving. Right now, what is my aim is to ultimately make you write a tremendous algorithm for each and every problem, not only bounded to this, but any kind of problem statement, and make you derivate the time and space complexity for a given algorithm, right? So that's what. Now, before going to the algorithm directly, some basic school formulas you need to understand, right? So this is most important. Formula number one. Usually, what is my aim is, I will not make you directly going to formula anything, whether it be a machine learning formula or a normal mathematical formula. By derivation we need to go. So let me ask you a question. What is 1 plus 2 plus 3 plus 4?
10.
1 plus 1 plus 1 plus 1.
4. 4.
1 plus 1 plus 1 plus 1 plus 1.
5.
5.
1 plus 1 plus dot 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 plus 1.
1. 1.
There are many ones. Assume that there are n ones.
N1.
So what will be the answer? If there are
N.
4 ones, you said 4
4 into
answer is
N
4.
into 1.
If there are 5 ones, you said 5. If there are n ones, what you will say?
1 plus n.
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 1 into n,
N.
not 1
N.
plus n, n. Yes, okay.
Yeah.
So what is the formula? If I have, this is formula number 1. It is sigma. You know what is sigma, right? Summation. Summation I is equal to 1 to n. I. Sorry, 1 to n, 1. What will be the answer?
N.
How many times you are summing the one constant one? N
10
times. So the
10
answer
times.
is n. Yes. So immediately say the answer for this also. C, constant C.
N.
N.
Some the constant can be 2 or 3 or anything.
N square.
N
N
square,
power C.
no. C. If it is 1, you say n into 1. So n. If it is 2, n into 2. If it is
C into
3, n into 3. So if it is C, n
N.
into C. NC. I can write it as NC. Right? So far, so good.
Yes, sir.
Yes. Third one is slightly different. Same on summation. I is equal to 1 to n. I put I inside. If I put I inside, what will come? What is I value now? I is equal to 1.
I square.
Next I is equal to 2. Next I is equal to 3. Like that it will go. Finally it will be 1. It is nothing but 1 plus 2 plus 3 plus dot 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 plus up to n it will go. So what will be the formula for this?
N into n plus 1.
N into n plus 1 by 2.
Arithmetic progression. You are saying the arithmetic progression, right? It is n into
N plus 1 by 2.
1 by 2. Very good. We will verify that also. For example, n into n plus 1 divided by 2. We have here 1 plus 2 plus 3 plus 4. This is nothing but summation I is equal to 1 to 4 I. That is 1 plus 2 plus 3 plus 4. I will substitute here. What is n value here? 4. 4 into 4 plus 1 divided by 2. So 4 into 5 divided by 2. 4 into 5 is 20. 5 2 is 10. So you got the result 10. So this result came. Similarly, you check for other values. This condition will work. Right? So it is very good, right? Easy.
Yes, sir.
Now I will save this. We'll continue this. Only 2 more formulas are there, but that formulas they give some time to understand. Very simple only, but we don't want to do that in 5 minutes. Okay. Now I'll go for attendance. I'll save here. So in this class we dealt about the remaining asymptotic notation. We had a revision for asymptotic notation. Then we came into the types of algorithms and we circulated into the formula going to be used for time and space complexity derivations. So far so good, right?
Yes, sir.
Yes, sir.
So far.